A global interpreter lock, or GIL. If you don't know what the GIL is, or if you've ever wondered why Python struggles so much with true multi-threading, or how the GIL affects your code, this video is for you. So grab your coffee and let's break it down. The global interpreter lock, or GIL, is a mutex, a mutual exclusion lock, that protects access to Python objects in CPython, which is the default implementation of Python. It's like a traffic light for threads in your program, making sure only one thread can execute Python bytecode at a time. To understand why the GIL exists, we need to rewind to Python's early days. CPython, which is Python's reference implementation, manages memory using a technique called reference counting. This keeps track of how many references point to an object and automatically frees up memory when the count drops to 0. But here's the catch: reference counting is not thread safe. Without some kind of lock, multiple threads could update these counts simultaneously, leading to crashes or corrupted data. The GIL was introduced as a simple way to make CPython thread safe. Here's how the GIL works in practice. Imagine you have multiple threads in your Python program. The GIL ensures that only one thread at a time can execute Python code. When a thread holds the GIL, other threads have to wait, even if they're ready to run. But wait, what if a thread is doing something slow, like waiting for a file to load or fetching data from the internet? The GIL can be released during these I/O operations, which allows other threads to run. The GIL's biggest drawback is that it prevents Python from achieving true parallelism in multi-threaded programs. Even on multi-core CPUs, only one thread can execute Python bytecode at a time. This means that for CPU-bound tasks like heavy computations or data processing, threads can't utilize multiple cores effectively. Instead, Python relies on process-based parallelism using libraries like multiprocessing to bypass the GIL. Each process has its own GIL, so they can run on separate cores. So what can you do if the GIL is slowing you down? Here are a few options. The first is to use multiprocessing. The multiprocessing library creates separate processes instead of threads, each with its own GIL, and this allows your program to utilize multiple CPU cores. The second option is to leverage C extensions. Libraries like NumPy or TensorFlow perform heavy computations in C outside of the GIL's control, so they can achieve true parallelism. The third option is to switch Python implementations. Consider alternatives like Jython or IronPython, which don't have a GIL, or PyPy, which optimizes performance for certain workloads. The fourth option is to try async programming. For I/O-bound tasks, Python's async I/O lets you manage multiple tasks without relying on threads. The Python community has debated removing the GIL for years, but it's not that simple. The GIL is a well-known feature and limitation of CPython, and it's undergoing major changes. With the acceptance of PEP 703, where PEP stands for Python Enhancement Proposals, the Python Steering Council has decided to make the GIL optional. And this initiative represents a significant evolution in Python's design, which opens up new opportunities for true multi-threading. The primary aim is to improve the performance of CPU-bound tasks while maintaining backwards compatibility with the extensive Python ecosystem. As of Python 3.13, Python now offers an experimental no-GIL mode that allows developers to build and use Python without the GIL. This feature is not yet the default, but provides a sandbox for developers to experiment and offer feedback. Developers can explicitly build CPython without the GIL using the disable GIL flag. And let's remember that Python's memory management uses reference counting and cyclic garbage collection to manage object lifetimes. Reference counting involves keeping a counter for every object that tracks how many references point to it. When the count drops to 0, the object is deallocated. In the no-GIL mode, these counters are updated using atomic operations to ensure thread safety when multiple threads modify reference counts simultaneously. Python's garbage collector identifies and deallocates objects involved in reference cycles, for example, two objects referencing each other but no external references. This mechanism has been updated to handle threads safely in a no-GIL environment, ensuring that the detection and deallocation of cyclic references do not lead to race conditions or corruption. And these changes address long-standing challenges with resource contention in multi-threaded applications, enabling concurrent execution of Python code across multiple CPU cores. While the no-GIL build enables true multi-threading, early benchmarks highlight certain trade-offs. Atomic operations for reference counting introduce some overhead, which can marginally slow down single-threaded programs. And in scenarios with multiple threads executing CPU-bound tasks, the no-GIL mode allows full utilization of all CPU cores, which offers dramatic performance improvements. By understanding the GIL, you can make smarter decisions about when to use threads, processes, or external libraries.